Hi, Mr. Duffy. Welcome to physics. Today our lesson is going to be about free fall acceleration. Now we've covered free fall acceleration in a previous lesson on constant acceleration. But since that lesson, we've learned about the kinematic equations. And what I want to do today is to refresh what free fall acceleration is and then apply some of the kinematic equations to free fall problems and work through some examples. So let's go ahead and get started. So just as a reminder, free fall acceleration is a type of constant acceleration in which case something is falling. We asked ourselves again, if an apple falls from a tree, does it accelerate? Think about these two questions. Would I catch that apple if it only fell 2 meters? Would I catch the apple after it's been falling off a very tall building? And you might again say to yourself, yeah, I definitely catch it if it fell from the tree from just 2 meters, but I might be a little bit more hesitant if it falls from the top of a large building. And then again, the reason why is because it'd be going a lot faster. Well, again, if you think about those in everyday terms, then yes, you would again realize that the object is accelerating. What's causing that acceleration is gravity. Gravity causes acceleration, and gravity is a force, which we'll cover again later in a forces and motion lessons. But for right now, we're talking about gravity causing acceleration. Gravity causes a constant acceleration of negative 9.81 meters per second squared. Now, the negative is there because that negative is indicating direction, and gravity always pulls down. So it's always a negative acceleration because we consider down to be negative. Okay? So gravity, again, causes acceleration of objects, and when gravity is the only thing causing the acceleration, then we consider that object to be in free fall. So again, an object that's falling is in free fall. Now, we know that's not exactly 100% true because when objects fall, they encounter air resistance. But for right now, we are ignoring air resistance. Again, later on in the year and later on in future lessons and future units, we will start to incorporate air resistance into our problems. But all objects, if air resistance is ignored, fall at the same rate. And that rate, again, is the acceleration of gravity at negative 9.81 meters per second squared. Now, again, we can see that in a picture here. We have an apple and a feather falling in a vacuum, and they are both falling at the same rate, negative 9.81 meters per second squared. So that was all covered in previous lessons, but let's take a look at what is new. We learned in our last lesson about the kinematic equations. Again, motion equations involving just studying the motion, not studying the forces involved. And so again, we came up with four main equations that we will be using throughout this whole year. Now, all these equations involve constant acceleration, and they can all be used for objects in free fall. And we actually don't even have to worry about the acceleration. If they are in free fall, we are going to replace all the acceleration values with g. So again, anytime you see an acceleration value in these problems, you can just replace that with g. G means the acceleration of gravity, and we know the acceleration for gravity is negative 9.81. So that's where these problems become a little bit different, is the fact that they don't even have to tell you the acceleration values, because if they say it's falling in free fall, you know what the acceleration is. It's not going to give it to you. So let's take a look at some of these problems. First problem we have is a ball is rolling off a table and it is falling towards the floor. What is the velocity? How fast is it moving after 3 seconds? So again, in these problems, what I'm going to try and enforce with this is we need to write out what's given to us in the problem. Okay, we want to find, so first off, we want to find how fast is it moving at the end of its motion. Its final velocity. Um, it's falling towards the floor, and the other thing that it gives us is a time of 3 seconds. It does not give us an initial velocity. It says it's falling off a table, so it's rolling off a table, or just dropping off a table. That would mean it has a velocity initial of 0 meters per second. Again, we're kind of interpreting that from the problem. And that's all it really gives us in the problem, but we also should realize that it is falling. It's in free fall. falling off the table. We're ignoring air resistance. So that tells us right there that our acceleration is negative 9.81 meters per second squared. Okay, that is the information given to me in the problem. Again, they didn't say the acceleration value, but it's understood since it is falling. Now, with that information again, we're trying to figure out the velocity after 3 seconds, after it falls again for 3 seconds. So the equation that I'm, with the information that I'm given, final velocity equals velocity initial plus acceleration times time. And I'm going to rewrite this though. Final velocity equals velocity initial plus g times time, since g is going to be our acceleration here, negative 9.81. Now, the next thing that I would do is draw a diagram, draw a picture of what's going on, but I've already got that. So again, I'm going to move into now plugging in some of my numbers. So my velocity final is what I'm solving for. My initial velocity is 0 meters per second, plus my acceleration, or my g value, negative 9.81, times our time of 3 seconds. So times 3. Okay, so basically this problem just boils down to negative 9.81 times 3, which ends up being negative 27.6 meters per second. Okay, and it's negative only because the direction, it's going down. Again, the negative means the direction. It's moving in the negative direction, so that is again indicating down. Okay, so again, not too much different than a other kinematic equation. We just, again, we're not given g in the problem. We have to know that since it's falling, g is um, our acceleration value. Take a look at another one. How far has the ball moved after 3 seconds? Okay, so again, same problem. The ball rolls off the table, but how far has it dropped? To do this, we would again need one of our other kinematic equations. But let's start by writing down again what was given to us. So the velocity initial was 0 meters per second. The time was 3 seconds. Our acceleration value is negative 9.81 meters per second squared. We're looking for our displacement. And another piece of information that we have from the previous problem was the final velocity. And again, we said that final velocity was negative 27.6 meters per second. Now, we actually have, again, more information than we actually need to solve this problem based on, again, having the answer from the previous problem. And that's where I would suggest that you take into account, well, what if I got the last problem wrong? Can I still solve it? And the answer is yes. And that's what I would encourage you to do, is not use the number from a previous problem unless you absolutely have to. If you made a mistake on that answer, if you didn't get that answer correct, then it's going to mess up the answer for this problem. And again, we can solve it without having that information as well. So again, we don't really even need the answer from the last problem to solve it. We just have to choose the right equation, kinematic equation. So the right kinematic equation would be our change in displacement equals our velocity initial times our time plus half at squared. But again, since g, gravity, gt squared. Now, another thing that's going to happen in this problem is the fact that our velocity initial is 0. So this first part of the equation is just going to cancel out. And that leaves us with just change in displacement equals half gt squared. We have all that information given to us in the problem, so we can, again, just kind of solve it. So let's go ahead and, again, I would draw a diagram, but we had a diagram on the last slide, so I'm not going to do that. Let's go ahead and just plug in our numbers. Change in displacement, our displacement is half of negative 9.81 times our time of 3 seconds squared. So half of 9.81 is 4.905, and 4.905 times 3 squared, which 3 squared is 9, comes out to 44 meters, 44.15, but let's just do 44. So our change in displacement is 44 meters. And that would be, again, it's negative because the negative 9.81. So again, that just means down. Okay, so again, this, hopefully you realize again that the problem could have been done, again, without our answer from the last problem. And again, I would encourage you to do it that way. Now let's think about what if an object is thrown upwards. The last couple problems and all the examples and all the things I've been talking about are things that are just falling down. But what if an object is thrown upwards? Is it in free fall? Do we consider that free fall? The answer is yes, because when the object is moving up or down, it is being influenced only by gravity. So if you toss an object up, gravity is pulling it, accelerating it in the negative direction. And you can see as it's moving up, the ball is getting closer and closer together. It's moving less and less distance. And then eventually it kind of comes back down and again spaces itself out again. Couple important parts on the graph, or sorry, on a motion problem such as this. You need to think about what is the object doing at the top. And when it's right at the top, that object is not moving anymore. What about its velocity right here at the end of its motion if you were going to catch it and right when you tossed it? What's actually interesting about that is they're the same. It has the same velocity at the beginning in the positive direction, or because it's going up, and a negative velocity, so it's the same, again, amount, but in the opposite direction as it comes back down. So if you threw the ball at positive 10 meters per second up, when it's coming back down into exactly the same spot, it's moving at negative 10 meters per second. Then another thing to kind of, again, realize when objects are moving up or down, they're being influenced only by gravity. And so they have the same acceleration the whole entire time. And I can show you that with a graph. So if we look at a graph of a velocity time graph specifically of the motion of the object, you can see again its speed is changing, which indicates that it's accelerating. And the fact that the line is a constant slope line, is the same, indicates that the acceleration is always negative 9.81. Again, the slope is always exactly, again, negative 9.81. When you look at this graph again, there's another thing to kind of realize is when it crosses the x-axis. That's at about 1.1 seconds. And what we can realize at that point is the ball is at 0 meters per second. It's not moving, it's stopped. And that would be at the top of its motion. So at 1.1 seconds, that's where the ball is at the top of its motion. It has slowed down to a stop, and now it is coming back down. So it's slowing down here at the on the graph. And then after it passes the top of its motion, it then starts speeding back up as it goes back down. So another thing that I can illustrate to you is something that I showed you in the last slide. Again, its speed should be the same. So again, if you toss the ball at, let's say that's 11 meters per second in the positive direction, if it took 1.1 seconds to get the top of its motion, it takes 2.2 seconds to get right back down to its the same spot in its motion. Again, if I follow that across, I can see that's at about negative 11 meters per second. It continues to fall after that point in time, but again, the speed that it was thrown and the speed that it is exactly when it ends back at the same spot is the speeds are the same. Their direction is different, but the speeds are the same. Now, another thing I guess I didn't really illustrate there is if it does again take 1.1 seconds to go up its motion, it takes 1.1 seconds to come right back down in its motion as well. These are things that again are happening in upwards and downwards motion. Now, let's take a look at a final problem. This problem, again, is one of the harder ones that we will do in this course, in which case, again, we're looking at something moving up and coming back down under the influence of gravity only. So Jason hits a volleyball so that it moves with an initial velocity of 6 meters per second straight upwards. We're not going to study things that are, again, moving at a curved path yet. So straight upwards. If the volleyball starts 2 meters above the floor, how long will it be in the air before it strikes the floor? Now, I would encourage you to set up this problem, just like we've set up any other problem, figuring out what is given to us in the problem, figuring out an equation we're going to use. We already have a diagram drawn of the motion, what's happening. But with this problem, you really have to keep in mind your positives and your negatives for your directions. So let's start off with what is given to us in the problem. The first thing that we have is an initial velocity, 6 meters per second. The ball starts with a displacement. So the displacement is going to be 2 meters above the floor. Okay. So its final displacement is going to be a negative 2 meters because it's going to fall down 2 meters. So the change in position is going to fall 2 meters in the negative direction. That's one of the things you guys, again, should watch for is that negative value. How long will the ball be in the air before it strikes the floor? So time is our question mark. But other thing, you can't solve this problem without one more piece of information, and that would be, since it is in free fall, the value of the acceleration is negative 9.81 meters per second squared. Again, negative because of the direction. Doesn't give you that in the problem, but something that you should, again, realize that you need to solve it. Now, with this information, again, we're looking for time. And we have no equation that just necessarily gives us time right off the bat. That there's not one equation, but we have to use an equation that does have, again, time in it. So we are going to use this displacement equals velocity initial times time plus half a t squared problem. That's going to allow us to solve the problem, but again, it's not solving for time directly. We're going to have to kind of like rearrange the equation to actually be able to solve for it. It's still okay. We can definitely do that. So let's go ahead and plug in our numbers now that we have that. So the displacement is negative 2. The velocity initial is 6 times time, which we do not have, plus half of negative 9.81 times time squared. So I think at this point in time, with using this equation, you might realize that we're not going to be able to solve it using our traditional methods. We have a variable in the equation twice, squared t squared once, and just by itself the other time. But I think if I rewrite the equation, you might recognize what we need to do. What I'm going to do is I'm going to combine some terms. Half of negative 9.81 is negative. I'm just going to do negative 4.9, and 6t again 6t. And what I'm going to do is I'm going to add 2 to each side. So I'm going to add 2 to each side. What that ends up leaving me with is an equation. 0 equals negative 4.9 t squared plus 6t plus 2. And when written that way, I think you can realize that we need to use the quadratic equation. To solve for t, we need to use the quadratic equation, which is fine. We can use that. So let's plug this into the quadratic equation. T is my variable, time, equals negative 6 plus or minus the square root of b squared, so 6 squared, minus 4ac, so 4a is negative 4.9, c is 2, all divided by 2a. 2 times a, which is again negative 4.9. Let's combine some of these terms. So let's again make it multiply and so. So t equals, again, negative 6, I can't do anything with that, plus or minus the square root of 6 squared. 6 squared is 36. 6 times 6 is 36. Minus 4 times negative 4.9 times 2. 4.9 times 2 is 9.8. So 9.8 times 4 is 39.2. So minus negative 39.2, which just becomes plus 39.2. All divided by 2 times negative 4.9, so that'd be negative 9.8. Yeah. Okay, now again, I can combine 39.2 plus 36. That becomes 75.2. So I'm going to erase that out. Square root of 75.2. And then I'm going to actually just do what is the square root of 75.2? It's 8.67. Okay, so here's what we've got. Negative 6 plus or minus 8.67 divided by negative 9.8. One of these answers is going to give us a positive time, and one of them is going to give us a negative time, which we also kind of realize you can't have a negative time, so only one of the answers will actually be correct. Let's go ahead and try them, get our two answers. So negative 6 plus 8.67 divided by negative 9.8 gives us a time of negative 0.3 seconds. Realize, obviously, that is not going to be our right answer because, um, again, it's a negative time. So let's try another way. Negative 6 minus 8.67 gives us negative 14.67, and divide that by negative 9.81, that gives us a time of 1.5 seconds. That one is our correct answer, okay, because again, it gives us a positive time. Negative divided by negative gives you a positive. So this is how we again solve the problem using the quadratic equation. If you didn't solve it using the quadratic equation, you actually could have solved this using two separate kinematic equations. You could have solved for the final velocity and then used the final velocity to allow you to solve for time in another equation. But again, this is possible. It did work, and we got the correct answer. You just have to use the quadratic to actually make it work, which again is something that you should be able to do. So hopefully you understand free fall acceleration a little bit better after this video, and you understand how to do some kinematic equations using free fall. Thank you for watching.